This talk is about uiCA, which is a performance analysis tool for predicting the throughput of basic blocks on recent Intel microarchitectures. I'm going to start with a brief overview over the field of performance analysis tools. So these tools take a piece of software and then they analyze the execution of the software on a specific hardware platform. And so there are tools for different kinds of software. So some tools, for example, analyze full applications, but there are also other tools that are more fine-grained and that analyze, for example, functions, loops, or individual basic blocks. The analysis itself can be performed in different ways. So there are, for example, dynamic tools that actually execute the software on the target hardware, and so profilers would be an example of such tools. And then there are also tools that analyze the software statically. And so there are, again, different types of such static analysis tools. So there are, for example, analytical tools, there are simulation-based tools, and machine learning-based tools. And so there are also tools that combine static and dynamic approaches. And then so these tools might produce different outputs. So they might, for example, predict the execution time or the throughput of the software, or they might show the resource usage of the software, or they might try to identify bottlenecks or hotspots. And in this talk, we are going to look at two static approaches, an analytical and simulation-based approach for predicting the throughput of basic blocks on Intel Core microarchitectures. And so in addition to the throughput, our tool can also produce some other outputs that we will mention briefly in the end of the talk, but the focus of the main part of the talk will be throughput predictions. So there are a number of existing tools for predicting the throughput of basic blocks on x86 systems. Like, for example, LLVM MCA, uiCA, the Intel Architecture Code Analyzer, or IDEML. And so the goal of these tools is to get insights into how compute-bound basic blocks are executed on a specific microarchitecture. So actually determining whether a block is compute bound or whether it is, for example, memory or I/O bound is not in the scope of these tools, and for this other tools can be used. Because the code is analyzed statically, these tools need a way to deal with information that is only available at runtime and that can influence the throughput. So the throughput can, for example, be influenced by the values that are initially stored in registers. So these values can, for example, affect the runtime of instructions with input-dependent timing, like, for example, division instructions. The initial register values can also affect whether two memory accesses are to the same address or not. And they can influence whether memory accesses result in cache hits or cache misses. Then the timing can also be influenced by the initial state of the hardware. So, for example, the state of different buffers, like the reorder buffer, or the state of the memory hierarchy or the branch predictor state. And finally, the execution time can also be influenced by interrupts or by interference from other cores. And so to deal with this statically unknown information, the existing tools make a number of typically optimistic assumptions that are justified by the fact that the tools are intended to only analyze code that is compute bound. And so these assumptions include, for example, that all memory accesses are cache and TLB hits, that there are no branch mispredictions, that no aliasing occurs, that during the execution there are no exceptions or interrupts, and that there is no interference from other cores. To evaluate basic block throughput predictors, in a recent paper, Chen et al. Proposed the BHive benchmark set that consists of more than 300,000 basic blocks that were extracted from applications from different domains, like, for example, numerical computations, databases, compilers, or machine learning. And so in addition to these benchmarks, they also developed a measurement tool that can measure the throughput in a way such that it is supposed to correspond to the common modeling assumptions of previous tools that we have seen on the previous slide. So this tool, for example, makes sure that the basic blocks are executed in a way such that there are no cache misses. Then Chen et al. Used their approach to evaluate the accuracy of several previous tools. And so they evaluated them according to two metrics, the mean average percentage error and Kendall's tau coefficient. And so Kendall's tau coefficient is a measure of how well the pairwise ordering is preserved. And so it is a value between -1 and 1, and higher is better. And so for the average error, they found that it lies between 9 and around 30% for predictions for the Skylake microarchitecture. And so at the beginning of our work, we were wondering how good an accuracy in this range actually is. So how difficult would it be to develop a predictor that is competitive or even better? And to answer this question, we have developed a very simple analytical throughput predictor that we can use as a baseline. And so this predictor predicts the throughput. And so here we assume that throughput is the average number of cycles per iteration when executing the basic block repeatedly. And so later in the talk, we will look at a more precise definition of throughput, but for now, this is sufficient. So this predictor predicts the throughput of a benchmark for the Skylake microarchitecture as the maximum over the number of instructions in the benchmark divided by 4, where 4 corresponds to the maximum number of microops that the Skylake microarchitecture can issue per cycle. Then it takes the number of memory reads that the benchmark performs and divides it by 2, where 2 is the maximum number of memory reads that Skylake supports per cycle. And then finally we take the number of memory writes that the benchmark performs. And so Skylake can perform only 1 write per cycle. And so if we look at this, then we see that actually this formula contains only 3 hardware-specific parameters, which would be the 4, the 2, and the 1 here. Now, if we evaluate our simple baseline predictor with the same methodology that we have seen on the slide before, then we see that our baseline predictor achieves an average error of around 17% and a Kendall's tau coefficient of around 0.77. And so maybe surprisingly, this is actually competitive with some of the existing tools, and so in some cases even quite a bit better. And so this brings us to the question that we want to answer in the main part of this talk, which is what are the sources for these inaccuracies in previous tools, and how can we improve upon them. And so we found that there are 2 main reasons for these inaccuracies. So one reason is that the models that these previous tools use are not detailed enough. And the second reason has to do with the benchmarking methodology that was used to evaluate these approaches. And so in this talk, we are going to look at both of these issues. And first, I'm going to present a new parametric pipeline model that is much more detailed than existing models, and that is applicable to all generations of Intel's Core microarchitecture. I'm first going to give you a brief high-level overview of how the pipelines of recent Intel Core CPUs work. So they consist of three main parts. So the front end is responsible for fetching and decoding instructions. The back end or execution engine is responsible for executing them. And the third part is the memory subsystem. So let's say that we have two instructions, I1 and I2, that we would like to execute. The front end will then fetch them from the memory and send them to the decoders. The decoders decode the instructions into one or more microops. So recent CPUs don't actually execute the instructions directly, but they execute simpler micro-operations instead. The microops are also stored in microop cache, so that if the same instruction is executed in the near future again, it doesn't have to be decoded again, which can be an advantage as decoding can be a bottleneck. The front end then sends the microops to the back end, where they are stored in the reorder buffer and in the scheduler. The scheduler keeps track of the dependencies of the microops, and it can start executing microop as soon as all of its operands are ready. And so this may happen out of order. And the scheduler executes a microop by sending it through a so-called execution port. And so the ports are connected to different functional units, like a multiplier or an address generation unit. And so the functional unit that a microop needs determines the port which it can use. And so in the same cycle, microops can be sent to each of the ports, but a single port cannot handle more than one microoп in the same cycle. At such a high level, the structure of the pipelines of Intel Core CPUs is well documented and relatively similar across different CPU generations. However, many of the details that are necessary for accurate throughput predictions are different between different generations, and many of them are unfortunately undocumented. So the question now is, how can we build an accurate throughput predictor despite the fact that many of the necessary details are unknown? And so there are two classes of such unknown details. So the first one are properties of how individual instructions are executed, and the second class are properties of different pipeline components. And so to deal with the first class, we built on previous work of ours, so uops.info. So this work was published at USPLOS 2019. And it describes an automatic way to generate micro benchmarks to measure the latency, the throughput, and the execution port usage of individual instructions. And so this information is necessary for building an accurate throughput predictor, but so it's not sufficient. So we need additional information about individual instructions. And so we extended our work such that it can also automatically generate micro benchmarks to measure additional properties, like, for example, how instructions are decoded, and, for example, related to micro and macro fusion, and other properties. And so you can find the result of this work on our website uops.info. For the second class of undocumented details, which are the undocumented properties of pipeline components, we developed micro benchmarks that we evaluate using our tool nanoBench. So nanoBench is a tool for evaluating small micro benchmarks on x86 CPUs using hardware performance counters. And so the tool is implemented in a way such that there's only minimal overhead for accessing these performance counters. And so in particular, it doesn't require any function calls or branches for reading the performance counters. And the tool is precise enough to benchmark individual memory accesses. The tool is implemented as a kernel module. And so this makes it possible to disable interrupts and preemptions while executing a benchmark, and it makes it possible to run benchmarks that contain privileged instructions. For our current work, we extended nanoBench with the option to perform cycle-by-cycle measurements, so it can generate a graph that shows which events happened in each cycle. The tool is available as open source on GitHub, and further information can also be found in a paper that we published at ISPAS in 2020. And we have created micro benchmarks to reverse engineer important undocumented properties of, for example, the front end, of how ports are assigned to microops, the details of micro and macro fusion, the details of how move elimination works, and many other undocumented properties. And so now we won't have time to go over all of these details in this talk, but there is a relatively large section in our paper that describes all of the properties in detail that we have reverse engineered. Now, combining the reverse engineered information with what was already known before, we have implemented a detailed CPU simulator that simulates how a basic block is executed by the CPU and outputs a throughput prediction along with some other insights into how the basic block is executed. And so our simulator supports all generations of Intel's Core microarchitecture that were released in the last 10 years. And the differences between these microarchitectures are specified with a set of parameters. Now, before we evaluate our simulator, let's look at the second reason for inaccurate predictions that, as we mentioned earlier in the talk, has to do with the benchmarking methodology that was used for creating the BHive set. And for this, let's first take a closer look at what throughput actually means. So throughput is commonly defined as the average number of clock cycles per iteration when executing the basic block repeatedly in a steady state. So, but what does it actually mean to execute a basic block repeatedly? So we have basically two options. So the first one is to unroll the basic block. So if our basic block consists of these two instructions, so an add instruction followed by a decrement instruction, then we can create multiple copies of it. And then so we execute the whole thing, and we divide the execution time by the number of repetitions to get the throughput. An alternative to this is to execute the basic block in a loop. So here the basic block ends with a branch instruction that jumps back to the beginning of the loop. And now if we run both of these options on a Skylake CPU, we can see that the first one is much slower than the second one. And so this is because in the second case, the microops are delivered from the microop cache, whereas they have to go through the decoders in the first case, which is much slower for this example. Now, a problem is that most previous throughput predictors are actually based on the second notion of throughput. So they assume that the basic block is executed in a loop, and so consequently they assume that the basic block ends with a branch, whereas the blocks in the BHive set do not end with a branch, and the BHive measurement tool measures the throughput by unrolling the basic blocks. So the measurements and the predictions are actually based on different definitions of throughput, which is one of the reasons for why measurements and predictions might differ. And to deal with this issue, we have created a version of the BHive set, which we call BHive L, in which the benchmarks end with the branch instruction, and we also have extended the BHive measurement tool correspondingly. And so we have created the benchmarks in BHive L as follows. So for each BHive benchmark B, we take one general purpose register Rx that is actually not used by B. And then we add a decrement operation for this register, followed by a branch instruction that jumps back to the beginning. And so for benchmarks in BHive that are very small, we additionally add a variant in which the benchmark is unrolled a few times in the loop, because otherwise the loop overhead might dominate the execution time. Our simulator actually supports both definition of throughput. So for basic blocks that end with the branch instruction, so the basic blocks in BHive L, it predicts the throughput according to the second definition, and so for other basic blocks it uses the first definition. Another reason for the discrepancies between measurements and predictions is that there is a relatively large number of measurement errors in the BHive reference measurements. So, for example, we found that there are more than 20,000 benchmarks that have a measured throughput that is smaller than 0.5 cycles per iteration, even though these benchmarks perform a memory access. And so these measurements are clearly wrong, because the microarchitectures that were used actually cannot perform more than 2 memory reads per cycle. And so there are several reasons for these measurement errors, and so the most important ones are that often the number of repetitions is actually too low to reach a steady state. The measurement code contains branch instructions that are in the critical path, which make the measurements unpredictable, and the CPU ID instruction is used for serialization, which is expensive and has an input-dependent behavior. And so we have developed an improved version of the BHive measurement tool that does not have these problems, and so the details of this are described in the paper. As discussed earlier, the goal of the BHive set is to contain benchmarks whose execution agrees with the common modeling assumptions that we looked at in the beginning of the talk. To achieve this, the authors of the BHive set used the following approach. So first, they extracted a large number of basic blocks from different applications, and then they filtered out blocks that violate modeling assumptions. We have identified several additional classes of basic blocks that violate such assumptions, and because of this, we also filter them out. And so this includes, for example, benchmarks with TLB misses, and benchmarks that contain unbalanced x87 operations or unsupported instructions, and benchmarks with input-dependent timing, which are handled inconsistently by previous tools. Now let's look at some evaluation results. So here we see the results for the Skylake microarchitecture, which is the microarchitecture that is supported by the largest number of previous tools. And so in our paper, you can also find results for 8 other microarchitectures. And so in this part of the table, we see the results for BHive U, which is how we call the original BHive benchmarks that do not end with a branch instruction. And in this part of the table, we see the results for our modified benchmark set in which the benchmarks do end with a branch instruction. For the cases in which the throughput definition that was used for the predictions does not agree with the definition that was used for the measurements, we show the corresponding entries in gray. You can see that for both variants of the benchmark set, the average error of our tool uiCA is more than an order of magnitude lower compared to the previous tools, and Kendall's tau coefficient is significantly higher and close to 1 for our tool. In this line, we compare the original reference measurements from the authors of the BHive paper with our improved measurements, and you can see that there is a significant difference. Now, finally, we show that several of the properties for which we reverse engineer detailed models are in fact important for accurate predictions, even though they were ignored by most previous tools. And we do this by evaluating several variants of our tool in which the corresponding properties are not modeled. And so here you can, for example, see that if we use a front-end model that is similar to that of previous tools, instead of our detailed front-end model, the average error increases by almost an order of magnitude for the loop-based benchmarks, and by even more in the case of unrolling. And you can see that in some other cases, the difference is even higher. So if we, for example, do not model the port assignment accurately, the average error even drops below the baseline in the case of the loop-based benchmarks. In some cases, our detailed model only leads to an improvement for one of the two benchmark types. So, for example, for the loop stream detector unrolling, which is a relatively obscure feature on which there's only very little documentation available. And you can see that this applies only to loop-based benchmarks, but it leads to an increase in the average error by more than an order of magnitude if it is not modeled. In addition to throughput predictions, our tool can also generate a table that contains the actual port usages of each instruction in the benchmark and also some other information. And it can also output a timeline that shows what happens in each cycle. The source code of our tool is available at GitHub, and you can also find an online version of the tool at uiCA.uops.info. So to summarize, we have seen a new open source basic block throughput predictor for recent Intel CPUs that is significantly more accurate than the state of the art. And we have shown that microarchitectural details that were considered to be rather insignificant by previous work are in fact important for accurate predictions. There are several possibilities of how our work could be extended in the future. So while we focused in this talk on compute-bound basic blocks, there is nothing that fundamentally limits our simulator to such code. So it should, for example, be relatively straightforward to combine our simulator with a branch prediction model to support predictions for instruction sequences that could potentially have multiple branches. It should also be possible to combine our simulator with a memory hierarchy model, and another option for future work would be to integrate our detailed model into full system simulators or into tools that combine static and dynamic analyses.